Hello, my name is Simon Kleiber and I'm from the Institute of Computer Graphics and Knowledge Visualization of Graz University of Technology in Austria. Today I would like to present to you our work on the immersive analytics of anomalies in multivariate time series data with proxy interaction. Nowadays, sensors are ubiquitous in everyday lives, be it for example in the Internet of Things, in industry or in automotive test systems. The captured data offers many opportunities for analysis and insight, and for example, by analyzing sensor data, we can better understand physical processes and behavior, we can monitor systems to ensure their safety and working states, and we're able to detect faults or failures and can react to changes and sometimes even prevent problems ahead of time. Often, these sensors capture data from behavior that expectantly repeats itself over many cycles. An example for such measurements is a motor durability testing environment. There, motors are measured over a long period of time and keep repeating similar patterns as cycles with the same expected behavior. For example, temperature, pressure, RPM, and emission are measured in such environments. Such test systems have a large amount of sensors and many repeating cycles. For example, a durability test run can run over 1000 cycles of 2 hours with 500 sensors at 10 Hz sampling rate. This is a large amount of data and there's a huge interest in finding certain behavior. For example, a deviation of the norm can indicate problems, faults, or failures which need to be addressed, and ideally ahead of time. Such a deviation can also be seen as an anomaly. It is important that engineers are able to find such anomalies ahead of time. In our work, we use a subset of data from such a use case, but also from a chemical detection platform. Now, to analyze anomalies, we need two different views on the data. First, of course, we need to view the time series of one sensor over multiple cycles to learn the expected behavior. Then we might be interested in the interdependencies between sensors. For example, if we found an anomaly for which we would need to look at singular cycles and see the time series of multiple different sensors of the same cycle. Furthermore, automated analysis is often challenging due to noise or phase shift in the data, so a combination of human exploration and analytics methods is often favorable. Lastly, to support exploration, we have to find an answer to the questions of where to look at, i.e. finding interesting and anomalous sensors and finding out when an anomaly might take place. Now in 2D, probably the most well-known technique for time-dependent sensor data are line charts. However, in 2D, direct comparison is difficult and there's a large amount of overlapping time series that can hide behavior. I have an extreme example to the right here. On top you see a line chart of multiple high-frequent time series of one sensor over multiple cycles. Unfortunately, the frontmost line is hiding others due to its high-frequent data. Alternatively, in 3D and more specifically in VR, we can easily change perspectives by moving our head to see the behavior of time series further back as well. You can see the example to the right here. Now, 2D approaches use abstraction and other techniques to tackle this problem. The visual analytics approach of Sushnik et al. Uses two anomaly scores and a correlation matrix to give an overview and lets users compare single time series for more detail. 3D visualizations offer an additional channel that can improve overlapping in 2D charts. However, their use must be considered carefully. For example, Fanea et al. Unfold parallel coordinates in a circular fashion to avoid problems over overlapping lines of regular parallel coordinates. We can see another way in which 3D can aid with the wall of space-time by Tominsky et al., who used a third dimension to display additional data on geographic data. The addition of a third dimension allows to convey spatial connectivity and a variety of visualization options. Now, virtual reality has had a leap in technology due to the increased interest from the gaming industry. There's a growing interest of commercial and industrial application to integrate VR in existing processes. For example, for designing cars or for medical training, where VR is able to reduce the need for physical prototypes for many applications. The growth of VR fuels a need for the exploration of analytics methods in VR such that users can have a unified system for their work. Immersive analytics is a research direction to re-evaluate the benefits of immersive and, in our case, virtual reality environments brought by the technological advances in the last 10 years. There exists time series visualization in VR, however, they have different goals. For example, Wagner-Filho et al. Visualized 2D trajectories and use the third dimension to convey time in their space-time cube. they can make use of natural interaction of grabbing and pinching with both hands to interact with the data. Steed et al. Also used the third dimension to display additional information in their VR 3D parallel coordinates chart. This additional channel can be mapped to time, for example, and different perspectives on the 3D parallel coordinate plot show different insights depending on whether users look from above, the side, or from the front. Evaluations on the affordances of VR have found that VR may be advantageous for showing structure in the data, for example anomalies, and have found that it is very engaging and that VR has the advantage of using more natural interaction metaphors that can reduce mental workload. In our work, we explore the immersive analytics design space for VR-based analysis and anomaly detection of time series data. I would now like to go into the details of our created system. The main goal for this work was exploring the design space of VR to create an exploratory analytics system for better anomaly detection and understanding of time series data. We want to use 3D line charts to make use of VR's improved depth perception and the possibility for more natural and intuitive interaction methods, like for example via proxies. Furthermore, we need fitting analytics tools to better support the exploratory workflow. Let's now go into the details of how we achieve these goals. First, the visualization of the data. We stack line charts next to each other to create what we call a wave chart. Every sensor and every cycle is assigned a color with a uniform distribution of hues. Since we want each displayed time series or displayed axis to be clearly visible, we randomize the assignment of colors so that similar colors are not necessarily next to each other. Dynamic shadowing of the engine further separates especially high-frequent time series from each other. Since sensor data can be large, we use shader-based methods to modify the visualization to ensure a smooth frame rate in virtual reality. Here's another example with very high-frequent time series that make it look like the wave chart is an area chart. Here we can see how cast shadows help with discerning the different displayed axes. Next, like I mentioned, we have two important views. Users can either view one cycle and all the sensor data of the cycle, like you can see on top, or they can view the data for one sensor over all cycles, like on the bottom. As you can see, viewing one cycle yields a very different view, as different sensors can have vastly different behavior. When we compare the data for one sensor over multiple cycles, we can easily see anomalies in the sensor data. Finally, we have given users a rolling average view. The value on every timestamp now is an average of the last 100 values in the time series. This view is able to better show variation in high-frequent data and reduces issues with phase shifts for analysis. Interaction VR is a topic with a lot of choice. We have set out some goals that we want to achieve within our system. Following the recommendations of Marriott et al., we tried to incorporate natural interaction metaphors to make 3D transformation of the visualization more intuitive and to reduce the mental workload of our system. We also want to provide a flat interface hierarchy with little interaction, such that tools are easily accessible and users only need few steps to reach all the functionality. We want to ensure that users can fit the environment and the layout of tools to their needs. Finally, navigation in VR has the potential to induce nausea or be confusing for new users. Batch et al. Have evaluated their systems and found that users remain mostly stationary despite being able to move around. Hence, we opted for a more stationary interaction where users do not need to move much and instead can move the tools around themselves. Following these goals, we have opted to use a proxy-based interaction. The proxy is a miniature version of the wave chart, and you can see it together with its settings to the right. Users have it at arm's reach, and it keeps a fixed size while maintaining the proportions of the wave chart. To reduce clutter on the wave chart, most interaction is performed on the proxy instead. When users pick up the proxy or scale it via the scaling handles in the corner, the wave chart can copy all transformation. This way, users can stay in place and move the visualization instead of having to move around themselves. The proxy also shows a heat map of currently displayed highlights, the source of which we will discuss later. It also lets users select a range of time that is shown both on the proxy and the wave chart. The proxy settings to the right lets users define some behavior and use different tools. Users can stop the copying of translation, can define access for translation, and can let rotation snap to angles or disable rotation altogether. This gives them more freedom when changing the transformation of the wave chart. The proxy setting also allows for using and enabling or disabling various functionality that changes the visualization of data or uses the range selection. To support interactive exploration, we have also added a few tools. First, we have a clipping plane. This plane can be set on the proxy and allows to vertically clip all data either upwards or downwards. This way, it is possible to focus on valleys and peaks in the time series and to have a flat plane to make comparisons. Next, we have filtering. With the range selection on the proxy, users can select a time frame and filter the displayed data on this time frame. This is especially useful for high-frequent data to see the behavior in more detail. You can see a short demonstration of it to the right. To make it easier to bring a certain location into view, users can point at the wavechart and slide the wavechart such that the point at that location meets their eyes. And finally, we have two objects that are placeable in the world, our settings panel and a hand crank. The settings panel controls the display data and shows all sensors and cycles. It allows triggering of sorting or saving of the data as well. The hand crank lets the users rotate the order of the displayed axes to bring different axes to the front, which act as a selection method in our system. Users can grab both of them from a tool belt that follows at waist height. Users can take out objects independent of their state or location and can insert the objects back into the tool belt if they don't need it anymore. This way, the tools are always accessible. Now, to help users in their exploration, we provide two kinds of provenance. First, it is possible to save the current view, for example, when finding something of interest. And secondly, the Sensors and Cycle overview on the settings panel keeps track of what the user has viewed or saved and displays it with symbols next to the names. A magnifying glass signifies that it was viewed, and the save icon is displayed if it was also saved. With these tools, users can explore anomalies by viewing different sensors and cycles, by looking around the data and with the mentioned exploration tools. However, to better support the exploration workflow, we have added some additional analytics tools for sorting, guidance and finding of anomalies, and to search for similar patterns as points of interest. Users can sort the displayed data based on different similarity measures. For a reference-based sorting, the frontmost axis serves as the reference and the remaining axes are ordered according to the Euclidean distance or to a compression-based distance. If users are viewing rolling average, then this is used for sorting as well. As we can see in this example, users can quickly find similar sensors in a cycle by sorting. And then we have our anomaly-based sorting. It is supposed to find anomalous points on sensor data in the sensor view. For the computation, we use rolling average values to make the computation more robust against phase shifts and high-frequent patterns. First, we sort the axes based on their Euclidean distance to a computed average instead of using a reference like in the other sorting methods. The axes are sorted in reverse order such that the axis with the highest deviation is in the front. To find anomalous behavior, we compute the standard deviation at each timestamp over all displayed axes. If a measured value is outside the lower or upper Bollinger Band, i.e. if it deviates from the average by more than 2 standard deviations, we flag it as being anomalous. All values that are flagged as anomalous are highlighted on the visualization, and together with the sorting, this gives users a good overview of the anomaly of a sensor. I have here two examples that show how the results look like. In front, you can see the computed average in gray and all found anomalous parts are highlighted. In this case, we are seeing a rolling average view, but users are also able to look at the normal view. Here, we can see that mostly only 2 cycles have anomalous values for this particular sensor. We also use this sorting to give users an overview of the anomaly of cycles and sensors. The Settings Axis tab shows small bars in red that display the percentage of anomalous values of the corresponding cycle or sensor. In Cycle View, the scores of cycles display the average anomaly of their sensors, while the scores of the sensors are respective to the currently displayed cycle. The opposite holds true for Sensor View. Alternatively, we can also show only the average scores over all cycles or over all sensors. Finally, our system supports a sliding window search. This is useful when trying to find similar patterns at a region of interest. Users can use the range selection on the proxy to select a time frame, and the selected time frame defines a reference window with which parts of the data with similar patterns are searched. The results are non-overlapping, and a maximum of 5 per axis are shown at once. The reference window that is used for the search can have two different settings. It can either be the same for all axes, in which case the frontmost axis is used as a reference, or it can be relative to the axis itself, where the reference window is different for every axis. For the implementation, we have used the Unreal Engine and an Oculus Rift Consumer version 1 for testing. We compute a simple adaptive compression on the data to reduce sampling in regions where the values do not change. Additionally, to improve load times, we convert the CSV files into our proprietary binary format that also saves pre-computed values the first time a dataset is loaded from CSV. On our test system, with a state-of-the-art GPU but an older CPU and an SSD, we can achieve 50 to 60 frames per second with 3 million data points. The animations and interactions run in real time, and most data operations like sorting, filtering, or changing the displayed data take less than 1 second to complete. Only the sliding window search can take up to 5 seconds. I would now like to walk you through an exemplary workflow in our analytics system. First, we set up our environment. We can slide the visualization into view. Here you can see the data, our interaction proxy, and its settings panel, and the tool belt where we first will set up our setting and hand crank tools to fit our needs at arm's reach. Here you can see how we can interact with the visualization, move it around, we can scale it. We can, for example, fix the rotations or snap them to certain angles. If you only want to move the data but not rotate it, for example, you can fix the rotation. If you want to slide it from left to right, you can disable the other axis while moving it. You can interact with all the user interface elements either with the fingers or with a ranged interaction, and you can disable the copying of transformations entirely. And now for the analysis. Our environment is already set up, so let's slide the data into view. By moving our head, we can gain a first overview of the cycle. We can see on the anomaly scores on the settings panel that cycle 3 seems to be very anomalous. So let's look at this one in more detail. We can, for example, filter into an interesting peak here and see what the data looks like on a smaller time frame. As you can see, the proxy copies the displayed information, albeit in a smaller resolution. By disabling the average scores, we can see which sensor of this cycle has a high anomaly. Let's look at sensor 11, for example. While we move it around, we can see to the left in the third row there seems to be a dip, so maybe this is an anomaly. We can use the clipping plane to look at the peaks, but also at the valleys of this sensor more closely. By simply rotating the clipping plane, we can reverse its direction. The rolling average gives us another view on the data. It filters high frequent information, and we can see this dip in the third row again. Let's confirm our suspicions by sorting the data according to their anomaly. We can see from the highlights on the proxy here and on the data, the third row has shifted to the front because it seems to be the most anomalous. As you can see, cycle 10 seems to be the culprit. Let's save this view and maybe look at cycle 10 in more detail. Here we see cycle 10 and its rolling average view, but maybe we want to look at the data in its original form. Let's slide sensor 11 to the front, the one that we selected before, and sort all the other ones according to the Euclidean distance. And now we have the similar sensors to the front. We can use a sliding window search to search for similar patterns on the data now. Our search results are highlighted again on the proxy and on the visualization itself. The more bright spots indicate where the original selection is located. Now for the future, we would like to add more guidance in the form of computed viewpoints and more focus on recommending sensors and cycles. We believe that a replay system would benefit the collaborative exploration of the data and would like to look into collaboration in general in more detail. And finally, we would like to evaluate our implemented system by comparing the performance of our system on 3D versus VR, but would also like to compare it to other approaches in more detail. To summarize, we have explored the visual reality design space to create an immersive analytics system for finding anomalies in time series sensor data. The system aims at providing natural interaction to support the exploratory analysis process and offers a set of exploratory and analytic tools to detect and understand anomalies in the data. This work was created within the VR for CPPS project and is supported by the Austrian Research Promotion Agency. I would like to thank our project partners, the Division for Visual Computing of Fraunhofer Austria Research GmbH and AVL List GmbH for our collaboration. Thank you very much for your attention.